Hey y'all, it's Miss Power. Reviewing for the Module 3 test with you on the internet. um, Here's a video of me doing the entire Module 3 review. Your group quiz is on Tuesday, November 1st, and your individual test is on Thursday, November 3rd. All right, let's do it. All right, number one, given the function x squared minus 5x minus 6, find the following. The first two things, these first two types, are when I plug this number in for x. Right, so this number is, I've got my function, which is something squared minus 5 times that same something minus 6. And this 3 says plug in a 3 every time you see x. Right, this negative 5 says plug in a negative 5 every time you see x. And so let's do that. 3 squared is 9. 5 times 3 is 15. 9 minus 15 minus 6 is negative 12. 9 minus 15 is negative 6. And then minus another 6 is negative 12. This is PEMDAS, right? Simplifying both of these, we're going to use PEMDAS. Parentheses, exponents, multiplication and division, addition and subtraction. Let's do it again. Negative 5 squared is positive 25. You should be careful about signs on this one. I'm definitely going to give you a negative one. Negative 5 times negative 5 is positive 25. Minus 6 stays the same. This is 50 minus 6, which gives us 44. Okay, so again, when the number is inside the function, you're plugging in that number 4x. However, when we see this instead, when we see if the function is equal to 0, we rewrite f of x. So every time we see f of x, we could have written what f of x actually is. And then we set it equal to 0. And now we're solving for x. This is what we've been doing at the first half of the unit, right? The first half of the unit is when we see things like this, we know we either need to factor, we need to use the vertex form, or we need to use the quadratic equation. I think the latter two are pretty overpowered, so I'm going to factor this. Over here, I've got x squared minus 5x minus 6 equals 0. I'm ready to factor because one of my sides is 0. Later in the review, I'll remind you that we have to set things equal to 0 before we can actually factor them, before we can do the quadratic equation, before they're pretty much useful at all. Now we're looking for two numbers which multiply to negative 6 and add to negative 5. I'm going to go pretty fast on factoring since it was a skill last unit, but if you want to, while you're watching this, you should pause it as soon as I say what we're going to factor. Try to figure it out yourself and then see what I say. So this is going to be x minus 6, x plus 1, which tells me that my final answer should be positive 6 and negative 1. Why did I change the signs? I changed the signs because I'm looking for numbers I can plug into these x's that will eventually equal 0. Right? If I plug in 6, I get 6 minus 6 is 0, 6 plus 1 is 7, 0 times 7 is 0. Right? Same for negative 1. That's the thing that makes this equal to 0. I don't want that same number. I want the one that zeroes things out. Okay. Oh no. This is not actually a problem. It just looks silly. But now it's perfect. Okay. This first page is actually kind of a doozy, all these ones, so we're just going to go for it. Simplify the following expressions. Don't be scared of I. And don't have negative exponents in your final answer. Those are the rules. Let's get going. For this first one, and for this one down here, I think that's the only ones. Yep. These are both adding like terms questions. So what I mean by like terms is 8 and positive 48 are just a number. So we're just going to add those two numbers. And then 9/3 and 2/3 are also like terms because we're just saying we've got 9 square roots of 3 and then also 2 additional square roots of 3, making for a total of 11 square roots of 3. We're adding those as if they were exponents, right? Same thing down here for the 17 plus 3i plus 2 plus 9i question. There's nothing outside of these parentheses that suggests that we should even have them, right? So we can actually do away with these parentheses immediately. get rid of them. They're not being used. And now we do like terms things. 17 plus 2 are both numbers, so we can add those. Plus 3i plus 9i is plus 12i. Can we go any further? Not really, right? One of our things is a number, one of our terms, it has an I in it, so we're just done. Over here, same thing. One of our terms is just a number, and one of our terms has a square root of 3. So we are finished. Next one. 25 minus the square root of a negative 16. If this were positive 16, we would just say it's 25 minus 4, 21. Boom, done. Right? But the square root of negative 16 is not 4, it is 4i. The 4 comes from the square root of 16, and then the square root of negative 1, or the square root of the negative sign, is the I. So anytime you have a perfect square, but it's 9, you do the same number, but you write an I. So we copy down the 25, we did not use it. We copy down the minus, we did not use it. We replace all of square root of negative 16 with 4i, and then we say, oh, we're actually done. These are no longer like terms. I'll come back to this one. No, I'm going to do it right now. Nice. Let me make this a little smaller and put it here. There we go. All right, and then this, we are going to extend. Oh, except that's going to look very silly. Wow, it should not matter this much to me, but here we are. It's mattering a little bit. Okay. When we divide complex numbers, off to the side as a note, and I write this every time, if we had something like 10 plus 5i divided by 10, then this would turn into 1 plus 0.5i, because we would just do 10 divided by 10, get 1. We would do 5 divided by 10, get 0.5. We'd be done, right? The test question is going to look like this. It's going to be number plus number times I. So we have it in a plus bi form. We'd be good. This is because this is a real number. It does not have any i's in it that we can do this. Our number right now has i's, so we cannot just split up the fraction. Instead, what we're going to do is we're going to do anything within our power to cancel the i's, right? So then this is 10 plus 5i. This is 7 plus 2i. I'm going to put parentheses around the top and the bottom just to keep things clean. Now I'm going to multiply by a number that will cancel the i's in the bottom. That number is called the conjugate of the denominator, and it's that we take the denominator, copy and paste it, but change the sign in the middle. The reason this helps is now when we do 10 times 7, 10 times negative 2i, 5i times 7, and 5i times negative 2i, this will just be a different complex number. This ends up being 70 minus 20i plus 35i, oh gosh, plus 10i squared. But the denominator is fascinating, right? So 7 times 7 is 49. 7 times negative 2i is negative 14. But then 2i times 7 is positive 14. So we're getting rid of those 2 i's, which feels great. And then 2i times negative 2i is negative 4i squared. So far, we have 70 plus 15i minus 10i squared. And we've got 49 minus 4i squared. We've almost gotten rid of all of the i's in the bottom. The other big note is that every time we see I squared, we can write that it's equal to negative 1. So I still have 70 plus 15i. That's a terrible plus 15i. Let's do it right. But now I get to say it's plus 10 because the I squared is as if I did 10 times negative 1 and became a positive 10. And at the bottom here, I get 49 minus 4 times negative 1, which is the same as plus 4. So in the top, we get 70 plus 10 is 80. 15i stays by itself. 49 minus 4 times negative 1 is 49 plus 4, which is 53. And then very, very, very final step, we split up the fraction like we were hoping to be able to do this entire time to get our complex number. Main thing is you're always going to multiply by the conjugate, and it's always the conjugate of the denominator. All right, let's keep going. This one's easy. I'm just going to do it real quick. Anything to the power of 0 that's not 0 is 1. Bada bing. I'm actually going to skip to this one first and then do this one. I think they're pretty similar. Right? So each of these, there's like 3 parts of this term. Oh my gosh, that scared me. Okay, sorry, y'all. Um, um, each part of the term underneath the square root here, the negative, the 25, and the x squared, has a different square root, right? So the square root of 25 is the first one I'll do. The square root of 25 is 5, right? So if we do square root of 25, we get 5. In the same way, if we do the square root of x squared, we get x, so I should expect an x in my answer. Here, the square root of negative 1, we're going to call that positive I, right? And thus we have what the square root of negative 25 x squared is, because we took them one thing at a time. Back here, same thing. A little more complicated, so maybe not the exact same thing. I want to think of 350 in terms of like squares, right? I know that there's probably a perfect square that is one of the factors of 350, and I can take the square root of that part and then leave all the leftover stuff that's not a perfect square underneath the root. In order to find what perfect square is secretly part of 350, I'm going to break it down into its prime factorization. Prime factorization is when I take any two numbers that multiply to 350. I'm going to do 25 and 14, and then I break those down even further. So 5, 5, 2, and 7. And then I keep breaking down those numbers until I have to use a 1 or a decimal. So like I can't break down 5 anymore because it would have to be 5 and 1. So I'll just leave it there. So with this breakdown, I see that 350 could have been written as 1, 2, 2 5s, and a 7. With x to the 5th, y to the 6th, and z to the 7th. What if I had broken it down another way? What if I had chosen 10 and 35? No problem. 10 is 5 and 2. 7 is 35 is 7 and 5. This is still 1, 2, 2 5s, and 1 7. Right? There's a lot of different ways you can break these down, and all of them lead to the right answer. Now, when I write my answer here, I'm going to write up a square root in the back to put all my like extra stuff, and I'm going to put some space in the front so I can put my squares. 5 times 5 is a perfect square, so I can bring it out as a 5 in the front. 5 times 5 is 25, and then once I take the square root, because it's underneath the square root, so I have to take the square root. Once I take the square root, I get a regular 5. Boom, out front. This x to the 5th could be written as 2x squareds times an extra x. The square root of these two is 1x each, with 1x in the back. Oh, shoot. I forgot. The 7 and the 2 don't have a partner, so they stay in the back as well. I can split the 5 into 2 groups of 2 and 1 left over. My 2 groups of 2 come out to the front, and my 1 left over stays in the back. I'm going to make this a little bit nicer, and instead of writing 2 x's next to each other, I'm going to write x squared. Same thing here. My group of 6 y's, I've got 6 y's, and I want to make them into partners, so there's 3 partners. So this shouldn't be a 6, this should be a 3 for the 3 partners, the 3 pairs that I could find out of 6 y's. And then there's no leftovers. For the z, there's also 3 partners, but there's 1 left over. And then to clean this up a little bit, 2 times 7 is something we know. So we'll make that 14. Cool. I'm going to do this one first, then this one, because I think they're basically the same thing. When I've got x to the 5th, y to the 8th on the numerator, x to the 3rd, y to the 7th on the denominator of a fraction, I can use my exponent rules, subtract these, do 5 minus 3 is x squared, 8 minus 7 is 1, and be done. We're finished. Great. If you remember that division means you're subtracting your exponents, go for it. If not, we can think of it as if we've got 5x's on the top and 3x's on the bottom, and I cancel as many as possible, how many are left over? 2. And are they on the top or the bottom? The top. So we can use that line of thinking to think, oh, we should have the x squared on the top of a fraction. Same thing here. We've got 8y's on top, 7y's on bottom. If we cancel 7 of them, there's 1 left over, and it's on the top of the fraction. This one over here is basically the same thing. We just need to rewrite it at first. All of the positive exponents stay where they are, and all of the negative exponents become division. Now, if I've got 12x's on top and 9 on the bottom, I cancel all of them but 3. Let me put it over here so we can actually see it. I cancel all of them but 3, and they're on the top. If I cancel 10 and 14, there's 4 left over, but they're all on the bottom. So this final answer should be x to the 3rd, y to the 4th. Some people will immediately say that it's x to the 3rd, y to the negative 4th, which is totally true, and a lot of people get that by adding these exponents. But then I would want you to put this in the final form because I don't want negative exponents. I want you to take that y to the negative 4 and make it a y to the positive 4 in the denominator. Whew, okay, first page done. Let's keep going. Switch between the following expressions between radical and exponential form. Exponential form will always be here like a fraction, and then radical form will have a radical, right? So I'm just going to set those up. Here, x to the power 6 stays to the power of 6, and the denominator of the exponential fraction becomes the root, the 13th root. So if this is our denominator, it goes into our root, and if this is our exponent, it stays as our exponent. We definitely could have simplified this one, though, because 12 divided by 4 is 3. Okay, here, the 13 stays where it is, and the 10 becomes the denominator. Here, the 7 stays where it is, and this is kind of a tricky one. There's no number here, and that always means a little 2. That always means it should be a 2. All right, there we go. Solve the following quadratic equations by factoring. Can do. So you'll, on your individual test and on your group test, sometimes I'll tell you exactly how you need to do the problems, and then mostly on the individual test, I let you do them however you want, right? Solve the following quadratic equations by factoring. The first thing we're going to do, and I'm going to move my work actually up here. I'm not really sure why I put that like that, but that's fine. I want to add to 8 and multiply to 15. Pause if you want your own time, but that's 5 and 3. And then my answers are -3 and -5 because it's the things I would plug in for x to actually make each factor 0. Same thing here. I want to factor. I can do this by saying what multiplies to -100s and adds to 0, which ends up being -10 and +10. This is also the difference of two squares, which is one of the special ones we learned in Unit 2. So if you remember the special rules, this will be a lot easier. And then finally, we've got this kind of nastier one. The big thing here, for me, is that it's not equal to 0 yet. And that's a huge issue, right? If we want to solve this by factoring, the very first thing I want to do is I want to subtract 10x on both sides. That's 110. That's very silly. I want to subtract 12 on both sides. And I want to get 2x squared minus 10x minus 12 is equal to 0. Let me tell my roommates not to make too much noise. No. I feel like y'all can hear them. Maybe you can't. Sorry, y'all. Great. Okay. Okay, so we moved everything to one side because we need it to equal to 0. That's a need. Now I kind of want this to be divided by 2 because I'm allowed to. They're all divisible by 2. 2 divided by 2 is x squared. Negative 10x divided by 2 is negative 5 squared. Or sorry, negative 5x. Negative 12 divided by 2 is negative 6. And 0 divided by 2 is 0. Now I can factor by saying what multiplies to negative 6 adds to negative 5. Turns out it's negative 6 and positive 1, which makes my solution negative 6, or sorry, positive 6 and negative 1. Again, the things that if I actually plug them in for x, they give me 0. Cool. Keep going, a couple more left. Solve the following quadratic equations by using the quadratic equation or with vertex form. So the quadratic formula or vertex form. I have a preference, right? Quadratic equation is something I'm going to use when this has a number out front. That's a quadratic equation question to me. Or to be honest, when this is odd, that's a quadratic equation one. Whereas the vertex form, it's nicer if this is even, which here it is. All right, I'm going to do vertex form first because I think it's weirder, and then we'll do quadratic equation. Let me... That wasn't even close to what I wanted. That's enough. Okay, if I want to make this into a vertex form, we remember that vertex form is when we have a perfect square, and then we have to say how wrong we were from our perfect square. We've got an x squared, so I'll put an x squared. Our negative 8x's, we can sort into 2 negative 4x's, remembering to split it all the way down the middle so that it's actually a perfect square. And then if this were a perfect square, this would need to be 16. It would need to be negative 4 times negative 4 to get negative 16. So far, I've got this part of my vertex form. However, I don't actually want negative 16 to be what's happening on this side of the equation. I want positive 4 to be what's happening. So I have to tell myself, from 16 to negative 4, how would I change it to actually make it into positive 4? I would minus 12. It's always going to be a subtraction or adding thing. Nice, I've got my vertex form. It's still equal to 0, so I'm still going to write equal to 0. Now, I want to solve for x. I want to get x totally by itself. To do that, I'll add 12 to both sides. I'll get x minus 4 all squared equals 12. I will then square root both sides. Get that x minus 4 is equal to plus or minus the square root of 12, which, to be honest, I can simplify because this is 2 times 2 times 3, so it means it's 2 root 3, plus or minus 2 root 3. That's like that one from the first page. And then I want to add 4 to both sides and get that x is positive 4 plus or minus 2 times the square root of 3. So whatever my 2x's, let's see. I'm realizing I need to give you all a lot more room on this for the quiz, so that's good to know. Boop. My 2x's are 4 plus 2 root 3 and 4 minus 2 root 3. It's one with the plus version and one with the minus version. So that's the vertex form. The vertex form way is you put it into vertex form and then you actually solve it for x because it's equal to 0. Make sure it's equal to 0. Over here, when we want to use the quadratic equation, we remember that the quadratic equation is x is equal to negative b plus or minus the square root of b squared minus 4 times a times c. all divided by 2 times a. What are our a, b, and c? In this equation, our a, b, and c are 4, 3, and negative 18. How did I know that? The a is the number in front of x squared, the b is the number in front of x, and the c is the number that's on the back. Okay, now I'm going to take my... Sorry, y'all. I'm going to take my a, b, and c. I'm going to plug them into my quadratic equation. I'm going to get negative 3 plus or minus the square root of 3 squared minus 4 times 4. Because the first 4 is just in the equation. The second 4 is the a. Times negative 18. All divided by 2 times 4. Again, the 4 being a. I'm going to simplify these as much as possible. Let's get out my calculator. Again, if you see my RJ pencil, please tell me. I love RJ a lot. I've got 4 times 4 times 18 is 288. And a negative times a negative is a positive. 2 times 4 is 8. Down here, we get negative 3 plus or minus the square root of 297 over 8. Then y'all aren't going to like this plan. But I'm going to simplify the square root of 297. I'm going to say it divides by 3, and I get 99. That's 9 times 11. That's 3 times 3. All of the pairs will come out front, and all of the leftovers will stay in the back. So I think this is plus or minus 3, the one from the pair of 3's, times the square root of 33, which is 3 times 11, the 2 leftovers. This is all divided by 8, which means that our two solutions are negative 3 over 8 plus root 33 over 8, and the same thing with a minus. So let me actually just put those in the x things over here. My solutions are 3 plus 3 root 33 over 8 and 3 minus 3 root 33 over 8. Great. Last one. Solve the following quadratic inequality. The way to solve these starts out the same way, kind of to graph it, basically. Nope. Oh, that's too bad. Again, sorry, y'all. Wow. Like, almost know what I'm doing here, huh? Okay, this starts out as if you're graphing it, actually, right? If I'm going to graph this, I'm going to factor this. I'm going to tell you that the function equals 0 when x is negative 10 and negative 2, because this should have been a positive 2. And that means these are my x-intercepts. The reason I'm going to graph this is so I can see when it's below the x-axis, right? If I want to know when this function is smaller than or equal to 0, it means its graph is below the x-axis. So I'm going to graph it by saying this is x equals negative 10. This is x equals negative 2. I know that my x-intercepts are at these 2 points because I factored it. And I know that this opens up because our a is bigger than 0, right? We don't have a negative number right here. So we know that whatever the vertex is, or whatever the y-intercept is, certainly our function will look kind of like this, right? So now we know it's below 0 down here, it's equal to 0 right here, and it's above 0 at all these places. So when I look at the x's when it's actually, so we want the x values that give us negative y values. These are all the negative y values. It's actually negative or 0 y values. So these are all the negative or 0 y values. So these are all the x values for which we actually got those. If we start at negative 10 and we end at negative 2, and we look at all of the x numbers, the x values in between those two numbers, we get values of the function that are lower than 0, that are below the x-axis, right? It's all of these ones. Whereas if we plug in numbers bigger than negative 2, we would get positive values. And if we would plug in values smaller than negative 10 for the x, we would get numbers that were bigger than 0 for the y. So we don't want those in our answer because we were asked for the negative values. Cool, y'all, that is the review. I'm going to post this picture so you have a copy of the answers. I'm going to post this video, and happy studying. I will see y'all tomorrow for your group quiz.